Shimon has been doing AI since before it was AI. It was computer vision, it was other things, and he has contributed in many different ways to the field over the years. And his talk today is actually going to be about image understanding beyond object recognition. Welcome.
Okay, so when we look at an image, complicated image like this, we get a very rich information getting out of that. We know what the objects are, but also we know what they are doing, we know what the situation is, what happened before, what maybe is likely to happen in the future, and so on. And it's pretty amazing. That's what all the vision people here, and of course outside, are interested in, to understand this almost miraculous process which lets us take something like this, namely a recording of light intensities, and eventually recover all this wonderful and rich information that we get. Now, in this process of understanding this retrieval of information or extraction of rich information from complex images, most of the work that has been done today has been primarily at the object level. It's not only, but I think it covers, it's a correct generalization that the advances that we had were primarily at the level of classifying objects. When we look at objects, we naturally divide them into some natural categories like dogs and cats and so on, and we are pretty good and we have pretty good theories that work at retrieving or extracting class labels of objects in the scene that we see. But the information that we get is also, we can sort of divide it into going way down below the object level and way above the object level, and I want to look a little bit into these and some of the implications of the fact that at these two levels, sort of below and above the object levels, we are not close to the kind of proficiency that we have in our modeling at the object level. Some example about below the object level, we look at this and we immediately see, is this boy smoking, yes or no? No, right, but to know this, we have to look at really specific details which we are immediately drawn to, and it all depends on this fine detail in the image. If we do not pay the right attention and extract the right fine detail, we will be confused and we will not know and notice this piece of information which obviously is very important and central in understanding this particular image. I already showed this image in which we have not just objects, but combinations and configurations of objects. So the meaning here depends not on just the objects, but on the higher level configurations. And very often, the understanding of the image depends on putting together all of these levels. We need the objects, we need higher level configuration of objects, we need fine details that happen in specific parts of the image. So for example, these are images which, after training network, for example, to recognize people hugging, first of all, the task is very difficult, but this was, for example, a false alarm in which it looks sort of like hugging, but it is not. We can even make a finer distinction that one of these embraces or hugs is a more intimate, a warm one, the other one is more formal, and so on. You will have probably no difficulty extracting this. And to get these distinctions, which are important behaviorally, we need to extract information or to integrate information about the objects, but also the configuration of different objects, and the configurations depend very often on fine details, like in this case, the exact shape of the hand or its position relative to the other person body, and so on. So we need to put together all of these levels quickly in order to understand the image and extract the meaningful information for us. And as we'll argue as we go along, I think that understanding all of these levels below and above the object level will probably require significant advances. It's not just more training, but serious changes and additions, and the additions may lead us into a more brain-like kind of models compared to what we have at the moment. So let me start roughly. I structured it as sort of below the object level, looking at important details, and going above the object level. As I mentioned, the main advances have been in sort of ImageNet type classification, which is very impressive to look at images like this and being able to recognize and classify correctly the objects in each one of these images. But humans have also, the human visual system is also very efficient in using much more limited information in local configuration, which are much more restricted than complete objects. And probably when you look at this, you can recognize each and every one of these sub-configuration. They don't need to be specific, well-defined parts of objects, but we can efficiently deal with and recognize these local configurations. And I think that in trying to model understanding of complex images, it turns out that the ability to recognize efficiently restricted local configuration is very useful, in part to minimize variability. When you look at these full images, we all see people drinking, but the images themselves are quite different from one another. It will not be very easy to generalize from one to the other. If you can also be good at recognizing local configurations, if you look at these configurations, we can already understand from the smaller one that these are people drinking, maybe even drinking from a bottle. But now the images at this level of the restricted, more local configuration, the images are almost a copy of one another, and it becomes much easier to deal with higher variability, occlusion, and so on that occurs in natural images. So we became interested in looking at the limit of the more local, simpler, reduced atomic units which you can still recognize. And we have conducted a psychophysical experiment that went like this. We show a subject an image, and what they have to see, just to label what the image is, a dog in this case. If this image is recognized correctly by a group of subjects, 20 subjects, then what we do is we create 5 descendants of this original image. Each one is reduced. 4 reductions are obtained by cropping the image at one of the corners, and the 5th one is by just keeping the entire image, but just subsampling it and making it reduced in terms of number of sample points. So in each case, the number of sample points is reduced. I will refer them roughly as pixels, but pixel, I don't really mean pixels. It's the number of sample points that you use. You need, in order to represent an image like this, it's an objective number of how many sample points you need. It's essentially twice the cutoff frequency in the image. And then if this image is represented by 50 sampling points, you can take the image and make it smaller, larger on the screen or smaller on the screen. It will contain the same number of basic sampling points. And you can always, if you made it larger on the screen, you can now subsample it again by just 50 points and recover the full information that you had before. So this is something objective, and when we start with, say, 50 pixels, we then test, say, images which are now only 48 by 48, and repeat the search over the entire tree. If any one of these is recognized, we reduce it further and create its own 5 descendants and repeat the process. So all of this was published a couple of years ago, and one point is, of course, that a technical point is that you cannot do an experiment like this in the laboratory, because each subject sees an image like this, and you can no longer ask the person to then recognize the sub-images after having seen the image and recognizing it before. So this is done online, requiring something like 15,000 subjects in order to complete the entire research on 10 starting images we started with. And now we're looking for the atomic, sort of the minimal, what we call the minimal image, which is the minimal recognizable image. And an image is minimal if the image itself is recognizable up above a threshold, which we took to take 50% of the subject, but none of the descendants are recognizable. And I'm mentioning 50%, but the interesting part that emerges out of this experiment is that this threshold is not important. There is a sort of phase transition, sharp transition at the level at which we go from the recognizable level, the minimal image, and then you make a small additional reduction, and the sub-images become non-recognizable. And let me show you some examples. You can participate in the experiment. I will show you first the sub-image, which is below this recognition threshold. Just raise your hand if you recognize the image. Don't say what you see, just show of hand. Just let's see how many recognize those. Okay, this image, raise your hand. Okay, how about this one? Okay, so if you looked around, I think in the last one, is anyone not recognizing this? It became from maybe 10% to 20% of the people in the audience to about 100%. The numbers that we get from a group of 20 subjects is, it drops from about 90%, 88 to 16%. Let's use this more for fun. How many people recognize this? Very few in the audience. Let's see now. Hopefully. Okay, a much larger number. And we look at them, they're really quite similar if you look at them. It's almost sometimes even difficult to see big differences between them, but one is recognized at 90%, the other one at 20%, and this is consistent, and that you get this drop at the level of the minimal images. I find it, by the way, interesting. It's not by the way, I think it's an interesting point by itself, which I will not go into, because this is a statistical, or this is a population response. Namely, it's not just that one person doesn't see it, and then with a better image, this particular person gets more information and sees it, but 93% of the population would recognize this, so it's just arbitrary people. Almost everybody, more than 90%, will recognize this as a horse. Nobody recognizes this as a horse, 3% in the population. So this shows that somehow we all carry out in our heads very similar representations of these objects, and almost, we cannot control over, but probably regardless of the particular experience, visual experience that people went through. And in this way, we manage with, for a set of images, 10 images, extract, actually, we know all the sub-images that are recognizable on their own. It's interesting, by the way, some of them are very local. It can be a very small part of the object. Some of them are more global, but the number of sampling points you need in order to recognize these images is, on the average, 20, regardless if it's a high-resolution, small part of the image, or a more global and low-resolution part. And we didn't encounter, you don't need more than about 40 sampling points or pixels to be able to recognize any of the objects we dealt with, and we compiled along the way sort of an interesting collection of sort of minimal images which has this catastrophic behavior or this phase transition, and it is now being used by a number of laboratories following up, looking both at the fMRI properties of these images, how efficient they are in actually activating specific brain regions, and a number of studies physiologically, one here at the Rockefeller, one at Harvard in humans using electrodes in epileptic patients. Now, it's interesting that these minimal images are very difficult for deep network to learn. In fact, in the experiments that we did with state-of-the-art deep networks, the results were relatively poor. They do not come close to image perception. They can recognize, they can recognize a pattern like this, but have great difficulty with things that we can recognize. They also do not show any catastrophic behavior, that there is any big change in the representation between here and here. Those who want to see all the details of the comparison with deep networks, they're all in great detail in this published version. But now we can go down, or we as humans go down even below this to a subatomic region, if you want, because if you look at this torso of a person or this horse head, these are minimal images, so reducing them even a little bit will cause them to be unrecognizable. But once we recognize them, we also recognize sort of a much more detailed internal structure of much smaller elements within this minimal image. These are some annotations that were produced for us by some procedure by people who looked at subjects who looked at these images, and you can see that they can annotate, they recognize, and you will see it on your own, that you recognize the thigh, the neck of the person, and so on. You can recognize the sub-details in the image once you recognize the configuration. And this, I think, is an important part of the vision process. When we look around, we are interested in extracting from pixels semantic information, semantic meaning information relating not about pixels and blobs and dark and bright areas, but about things that are out there in the world, and the things can be sometimes very small and detailed, sometimes complex configuration. We want to be able to extract all of them and understand them. We became interested in this, as that's again in the same comparison that done with existing deep networks. Getting this internal structure of the finer detail proved to be even more difficult than trying to classify the minimal images themselves. I'm showing you some results from a model that I will not describe in any detail, but a model that tries to dive in and make a full recognition of the internal structure of these minimal images. The details are in a fairly long paper just appearing recently in Cognition. I will just, for those who are maybe interested, just in one slide tell you roughly how it works. We do use deep neural networks in order to extract for us candidates for the internal components of the images. For example, this is what we obtain from the network trying to predict where is the eye of the horse. And I'm showing you C examples, some of the contours, the neck, and so on. So we get a bunch of candidates for each one of the internal components within the image. And then we have a second stage which tries to find a configuration, sort of select one eye, one ear, one neck contour, and so on, that together will make the best sense as a correct configuration that matches similar configurations seen in the past, and we get something like this. And this is now being applied again in our modeling across these ranges of different levels of detail that I said before, trying to recognize hugs from non-hugs, and trying even recently to be able to recognize the tone of the interaction, whether we are looking at a more intimate or more formal hug. What this requires, getting in these images, performing this internal fine interpretation in order to be able to inspect the fine details and make the conclusion. So this starts to combine, in our modeling, some sort of bottom-up deep networks, followed by a second stage which is more top-down in nature. But in getting into this top-down, I'll leave this domain of below the object level, and I'd like to switch and talk a little bit about some things sort of above the object level. So we had this image of a complex configuration, and what I'm going to describe now is things which are ongoing work. Some of them are partially completed, but none of this is really completed, none of this is published, but the challenging problem of understanding complex configuration in a scene which involves multiple objects, agents, objects, their interactions, and so on. And of course, in looking at such images, it's not enough to recognize the individual objects, have a list of the objects involved. If you knew that in this image there is a person and there is a piano, this of course does not tell you the complete story of what's happening in this image. There is some danger depicted here, there is some danger here, and we can extract these things, and so the understanding of the image goes way beyond listing the component objects in the image. And this is something that already is extracting or attracting considerable interest, and people are trying to do this, including in models relying on sophisticated deep convolutional networks in a variety of ways. People are testing, developing, and evaluating the ability of models to extract this compositional high-level information in a variety of ways. The one which is most commonly used is the automatic production of image caption. So you see an image and you have to provide a sentence in the language, in English say, which is a brief, adequate description of the image that you're seeing. So for example, these are automatically produced captions by computational models. You can see here a herd of cattle in the field, a kitchen with steel appliances and so on, which looks fine, looks nice, and in fact certain things can work, but with limited success. And we can argue it's very difficult to evaluate this in detail. In my view, really limited success, although certain captions look nice and natural, as you saw before. This is, for example, this is caption bot by Microsoft, and there is one by Microsoft, there is one by that Google has developed. I'm sure Facebook has something similar. But the automatic caption here, for example, is a brown horse standing next to a building. Now, this is, on the one hand, this is nice, it's correct, there is a brown horse and it's next to a building, but of course it misses what we will consider as the more interesting and central salient aspect of this image. If you look at this image, the automatic caption was even less impressive maybe. It's a group of people standing around each other. The small thing is it's not completely grammatical, but even if it were grammatical, it's certainly missing what's important in this image. And in running, this is part of a pretty large-scale psychophysical experiment, again, that we are doing, which follows the process of interpreting these images by humans as a function of time. We show an image like this to a large group of subjects with different presentation times, showing it just for 50 milliseconds, followed by a mask, 75 milliseconds, 100, 125, 200, 500, and so on. So different people see these images for different amount of time, and we try to develop the process of how the information is being extracted from such images over time. When you show it for a sufficiently long time, then essentially everybody comes up with very similar, they do not necessarily use exactly the same words, but they come up with equivalent descriptions of what happens here. Here is just a quote from one of the captions given by a subject in this experiment with long presentation time. Two women, he says, that not everybody catches that there are two women here, but two women sitting at a restaurant table while a man in black shirt takes one of their purses off the chair while they are not looking. So a long description describing everything that is happening here. And if you look at it, it sort of uses what I would think, and many people I think in cognition would think, it's sort of the natural language of cognition. You describe what's going on in terms of the components in the scene. There is a man, a woman, a purse, a chair, their property, the man is young, the purse is red, and primarily binary, not necessarily binary, but primarily binary relationships between components in the scene. For example, that the man is grabbing the purse, that the purse is hanging off the chair, and so on. So that's the kind of description that you get out. You can also describe it as a sort of a graph which gives you the various components. Each one of these nodes is a component that was identified in the image, the elliptical one. Then you have properties, and then you have some arcs in this graph denoting the relationships that were noted by the subjects looking at, perceiving and describing these images. And when you look at what different subjects give you, the exact order of the words in the sentence and even the individual nouns, it can be a bag, it can be a purse, and so on, but basically they all report back this basic structure as what's happening in the image. So this is what vision produces for us, and we can also identify this image under this description with the event of stealing occurring, and the stealing in fact takes time to develop. I will show you something about time development of these images in a minute, but it's interesting that you first get a representation of this graph as an output, and then two additional things happen relatively late in the interpretation process. One of them is that people start to note that the woman is the owner of the purse. And if you think about it, there is some inference going on because the woman was not holding the purse. She's sitting on a chair. The purse is hanging off the chair behind her, and so on. But we, based on our now knowledge of the world, we know that this situation in this situation, there is a the correct relationship, but it's very specific to our culture and our behavior and the way what we do with a bag when we sit down and we don't want to hold the bag, and so on. And typically the last thing that is being noticed, so I think that this ownership is now added relatively late because it's probably related to some more cognitive quick inferences that you make while you have this the image in front of you and while you've already extracted the basic participants and relationships. And the last thing that typically happens, that the last thing to note is that the woman is not looking at the man. And this, if you think about it, this is really an important part of the interpretation. If he holds the purse, maybe he's putting it back on the chair for her or something like that. But then the crucial aspect, distinguishing between the possible interpretations, maybe not 100% guarantee, is to see whether or not this act of grabbing the purse is done with the owner being aware or the owner is not aware. So basically we are testing something more general and abstract about stealing, that stealing is an agent takes an object, but somebody else is the owner of this object and the owner is not looking. You have to somehow get all of these things out of the image, put them together in order to now understand or retrieve the abstract event in this image that a stealing took place. And once you construct it in this way, I think that it's the only way to really reach generalization of recognizing such images. It's not a repeating occurrence of here is another image which is sort of similar to images I've seen before. The other one was stealing, so this is stealing as well, but it's putting together this information in order to make the conclusion. So in other modeling, which is now under construction, the process that we are trying to model sort of has two components. One is more visual, and the other one is more cognitive, where we store our prior experience and memories and what we know about the world. In looking at these images, the first pass that occurs is sort of from vision to cognition. This is what the deep networks would do for you, for example. You look and you start to extract primarily a number of objects, typically initially a small number of objects from the image, but you may notice a bag, a chair, a woman. So this is the pass from vision to cognition. But then you also, once this occurs, there are some processes which are not primarily visual and are not, in our modeling, part of this direct route from vision to cognition, but it's something that takes place within processes that are running within these higher level brain areas, the more cognitive brain areas, which puts together, they put together the bag, the chair, and the woman to add a new relation in this graph that you extracted, that the woman is in fact the owner of the bag, and this is added to your ongoing interpretation of the image. But then you also have to make sure it becomes now imperative to take something out of the image which is specific, and you may have not done it otherwise, and this is to make sure to test whether the person grabbing the purse is or is not within the field of view of the sitting woman. So you sort of try to direct the visual system to now pay attention or extract primarily this piece of information that is missing the direction of gaze. The vision part now ascertains that she is not looking, and from this now it completes the interpretation that what you see in the image is a person stealing a purse that belongs to the woman. So I think that these two components, the visual and the more cognitive one, both need to be modeled correctly, and the interactions between them, and what happens during the interpretation of a complicated scene and not just naming objects, is that you have a pass from vision to cognition in which you can retrieve objects, some of their properties, some of the relations. Then you have processes running within the cognitive part on its own, sort of independent with the visual part for it, and this leads to the inferring about additional properties and the relations in the image. And then finally, you have the top-down part from the more cognitive components of the system to the visual ones, which can direct it, and that's an interesting, I think, operation, the ability to be able to direct the visual system to tell it what to extract and maybe where to extract, so it's both spatial attention, but also what to extract from the image, and this completes the loop and allows you to make the full interpretation of the image. Let me show you, and I'm getting close to finishing. I wanted to show you what we get psychophysically when we look at the temporal interpretation, how things develop with time, and you can appreciate that it's sort of consistent with this cycle of things that you get the visual to cognition, some partial interpretation, and this directs the further evolution of the interpretation process. Here's an image, and when you look at it, you probably see, and you can describe what you see, and you will not be surprised that what everybody does after sufficient time is, here is one description, that a little girl with brown hair pouring liquid through a red funnel into a green bottle. You'll notice, by the way, that the first thing that you are talking about the girl, or let me just jump and show you, this is the timeline of these pouring images. When you show you after 50 milliseconds, the only thing that you get consistently is just the child. People tell you, I saw a child in the image. They cannot tell you anything more, but they say child. It's interesting, by the way, because there is this red, bright object in the middle of the visual field at fixation, but it's ignored. Everybody says there was a girl in the image. It takes slightly longer. It's 75 milliseconds. They say that not just the name girl, but the girl is holding something, holding an object. 125 milliseconds, she's pouring. 200 milliseconds, the funnel comes only after 200 milliseconds. She's pouring it through a funnel. And finally, and this takes quite a bit longer, into a bottle that comes later. So this is consistent, and people develop, the interpretation evolves in this manner. So to finalize, I think that in getting to circuits and the canonical circuit and what's happening, I think that we have a part of the system is the sophisticated vision to cognition, creating the representation and extracting the initial information from the image. What Jim DiCarlo talked about, the core object perception that takes place within maybe the first 100 milliseconds or so. But equally, you have within the visual system sort of a complementary network that is guiding the processing that I try to describe briefly, going in the opposite direction from cognition to vision with the interactions between them. And when you have more time to look at the image, not just this initial wave of feed-forward processing, the fuller image understanding is obtained by sort of an iterative cycle that goes from vision to cognition and then back from cognition to vision, sometimes a single cycle and sometimes more than a single cycle. So about canonical circuits, and with this I will stop. If you are looking for some canonical things that repeat themselves and provide sort of the repeating elemental structure to sort of functional, the minimal units of the functional circuit, whatever they are, I think that it's useful to think about them, and you will have to encompass not just pieces of the feed-forward network, but there is a circuit that requires to put together the two components of the parallel components of the part of the circuits going up and the part of the circuit going down, with interaction between them. I think that it will be challenging. I described the more visual components, and that there is a higher level, more fuzzy cognitive component, but I think it's certainly there. Probably the circuits are the same. Models that we have so far are coming from older AI, treat cognition usually in a very different way, or it's difficult, or we do not have at the moment good model that we use similar networks in the same language of successful language of networks that we have now for the vision to cognition part. They should be applicable, similar circuits should be applicable to the more cognitive part as well. So I think it's, in this sense, it's about time to have a second round looking at the more cognitive components, going beyond good old AI and trying to think about this in the language of networks. And I think it will be highly useful in thinking about the local circuits that do the computation together with the combination of perception and cognition that I talked about. I would like to just put the names of the collaborators. I will not go through them, and the funding agencies, the ERC, ISF, and a little bit from MIT. And let me stop here and thank you and take some questions. Thank you.
Dan.
So it's not just time, but it's also sophisticated priors that make this a very daunting task for AI or indeed for humans. For instance, the person holding the purse was wearing all black. If this is a restaurant, perhaps that was a server who was picking up a purse that had fallen on the floor, an event which is more common than having a purse stolen at a restaurant. Alternatively, it could be a companion of the woman. They have finished their meal, they're just about getting up, and he's aiding things by holding her purse while she does so. How do we incorporate sophisticated priors about human interaction into something like this, and how long does it then take for they're building the model?
Yeah, it's a good question. At a more minimal level, I would say that even without distinguishing this, I think if somebody told me, or if you would see that a certain fraction of the population, which didn't happen in this case, by the way, everybody agreed that it was stealing rather than something else, that there were some sufficient cues for that. But what I would say about this, is that it will be an equal, some of the images may be ambiguous, for example, and it will be okay if some of the subject would think that it's stealing. Other ones may be leaning towards the maybe picking up the bag interpretation. In either case, this interpretation need to be picked up. Some of them are more ambiguous and may lead to two different interpretations. But I think, regardless of this, I would be equally happy at this point with a model that produces these two interpretations and remains a bit ambiguous about them. It's also interesting, as we see in, for example, in the hugging example, that sometimes small details that are very difficult to find are crucial about it. The exact way in which the hand is placed over somebody else's body can be very subtle, but it tells us between the tone of the interaction. I will just say quickly that we combine this work with the work on the minimal images that I said before, because the minimal images are a very useful tool for discovering, if you wanted, to isolate important features that help you the interpretation. Because if you remove a few pixels for the image and suddenly the entire interpretation breaks down, then you have a guiding search possibility of looking at how you affected the image by making it from a minimal image to this sub-minimal images which are no longer recognized. And I think that it may be even possible to isolate what are the visual cues for the exact social interactions, what happens in the restaurant, and so on, using some techniques borrowed from the minimal image study. Oh.
Esther, last question. No, Esther, then Nico.
We've heard a lot about the ventral stream, the ventral visual stream through IT for identifying objects, places, persons. But we haven't looked at the dorsal stream. And what came to mind when I looked at your pictures was mainly vision for action. And Giacomo Rizzolatti studies of mirror neurons, where neurons that are excited by visual stimuli are the same ones you use for doing those same actions.
Yeah, I think that's a good point, and I think that the dorsal stream should be included in modeling of the visual perception, visual interpretation of images. I think that here maybe the action of grabbing, for example, may be done with participation of parts of the dorsal stream. I think that it may also be using some parts which may even not be entirely visual. So, for example, we know a blind person, if you ask a blind person what stealing is, they will tell you exactly what a sighted person knows about stealing. It's an agent taking an object that belongs to a second object without the other one noticing. Experiments like this have been done, and people come with identical sighted and non-sighted people. So I think that the knowledge about ownership is actually maybe unrelated to vision. It's in some cognitive areas which combine information from different sources, which abstract them, and it's no longer a particular visual area which also plays in this game.
On the left here, down below.
Hi, thank you for a great talk showing that scene understanding is a lot more than just object recognition. My question is a little bit related to the first one, and it's basically about this idea of priors. So it's really nice that you can sort of tease apart the timing with the different stimulus durations of what people can extract. And there's some really interesting work from Michelle Green, who's shown that the overall probability of the scene is also has a really strong influence on these timings. So I think the example from the paper is that, say, a pillow fight in the street is recognized. People need much more time to recognize even the basic elements in such a scene than in a pillow fight in a typical setting, for example. So I'm wondering how can the brain have access to that information so early on? That's what I find very puzzling.
Yeah, I think that's right. I would just make a small comment that I think that some people talk about priors, and I would just want to emphasize that these are very structured priors. It's not just the probability that, and these are important too, that a fire hydrant is not usually found in a kitchen, that probability is relatively low, and that's fine, and that there are some association and combinations between objects, but we also use some much more sophisticated information about direction of looking and about grabbing and about interactions and so on. So these are very structured priors. I think that this is really quite open. I think that's why I put it here, but it's a grand challenge. I think that understanding scenes is way, way beyond recognizing objects. It involves many more components of the system. It requires certain iteration. It doesn't happen in 70 milliseconds. So rather than giving you a satisfactory answer, what I'm saying is that I think that we are looking here at something which is very large, complex, but I think that was my proposal, and we are looking at it. I think that each one of these components are doable and understandable, and for example, we are now really concentrating on what it would mean that you want something from the scene, and this does not happen in, say, feed-forward networks. You want to say, I want to know who is to the right of the person with the yellow hat. Quickly I get it. I can guide the visual system to give me the information that I want. So this is, for example, a component that I think that if we understand it better, we will have at least some parts of this combined integration of going vision to cognition, within cognition, going back and iterating this process. But it will be a long journey.
Nico, you stand between us and lunch. Make it good.
Shimon, inspiring talk. You talked a bit about the bottom-up and the top-down. What kinds of inference algorithms do you think of when you imagine this process with these highly structured, this abstract knowledge coming in, but also the efficiency of a feed-forward convolutional neural network?
I think the efficiency of the forward is great, because I think we can train neural networks on more visual attributes than we usually do. Some people try to do it. I mean, not just names of objects, but you want to know, is the person touching the object or grabbing the object, for example. It should be possible to just get it from the trained networks, and they will not just tell you there is a person and there is a bag, but they will make quickly the fine distinction between touching and grabbing, which may be very important in certain situations. So I think we can milk much more we can train feed-forward deep networks to do much more than naming objects. They can name many other attributes that are important, but they will not by themselves. I do not think that, this is my belief, you can really train it satisfactorily on stealing by showing them 10,000 examples of stealing, it will not be a sufficient output to say, I saw this image, the image contains stealing. You want to know who stole, from whom, what was the object, and you really want a structured, full representation out. As I said, I think that we are working now, since we are more interested in vision, I'm focusing now more on the way in which the cognitive system can in a flexible way, guide the visual system to extract whatever you want and have something like this in the system. And as I said, I think that we have to think more about what happens within the more cognitive areas. People started to look at this, but how do you do more cognitive, abstract inference at the network level? I think we do not have yet very good models for that. I think that the language of trainable networks prove to be, I see it not just that DNN work well, but I think it shows us that working with networks and so on, and in this language and trying to build models in this way can be very fruitful and should be applied, I think, more seriously to the more abstract cognitive levels as well. And then it will become a more uniform, more shared canonical circuits in all of these parts that together will explain to us better how the whole thing works. But as I mentioned, it's a big challenge.
So let's thank Shimon and all the speakers.